So now that we have Laplace transform and inverse Laplace transform, so we can jump between these two spaces, let's look at the applications in which we're interested in. And let's look at something that we have seen a bunch of times already, but it's our base case. Let's look at homogeneous linear constant coefficients ODEs. So this is a second order. So we're taking the second derivative of y plus 2y prime plus y equals to 0. And we have some initial conditions on y at 0 and the first derivative of y. So we apply the Laplace transform on both sides of our ODE. And to make the notation simpler, we're going to use the notation that the Laplace transform of small y is capital Y. So let's look into it. Let's remember the Laplace transform of derivatives. So the Laplace transform of the second derivative, let's start with the first derivative. The Laplace transform of the first derivative is Sy, capital Y, minus the boundary condition. So we know the boundary condition, so we can just introduce that. And the Laplace transform of the second derivative is x squared s squared ys minus s times y at 0 minus the first derivative of y at 0. And we know the boundary conditions, so we can replace those values. So we go from our system, like our ODE, second order linear constant coefficient, and our two boundary values, to an equation on ys. Look at the fact that here we don't have any derivatives anymore. So we can just solve it for capital Ys in a fairly trivial way, and which we retrieve a big fraction. So if we can compute the inverse Laplace transformation of capital Y, we're good, because we know that, well, capital Y is a Laplace transform of our solution, so the inverse Laplace transform of capital Y will return us exactly the function we're looking for. So let's try to do that. So we're looking for yt is the inverse of capital Ys. It's the inverse of this fraction. To simplify, we'll just call the two coefficients on the denominator, we're just going to call it a and b, so we have an easier notation going around. And I want to introduce a new trick that is going to be very useful when doing inverse Laplace transform of fractions. This is called a partial fraction. The general idea is to break a bigger fraction into smaller terms that we can handle in an easier way. So for any fraction, you can rewrite a fraction as a sum of simpler fractions. I will post partial fraction videos on Canvas, so you can follow that for more information on how to do that. But the general idea is that if you have some polynomial as a denominator and as base a product of monomials, then you can split it as single constants divided by each denominator one at a time. When you have repeated roots, so here we have s plus 1 squared, then you have to deal with the fraction with s plus 1 and the fraction with s plus 1 squared. But you gain the fact that now you have capital A and capital B and no dependency on s on the top. So how do we find capital A and capital B? The most straightforward way that we can call brute force is just by trying to solve the equation for a plus b. So we multiply b by s plus 1. Now we have one huge fraction on the left. We set it equal to the fraction we had at the beginning. Then we solve for it. And we have capital B equals small b and a plus b equals to a. Why do I call it brute force? Because on one hand, it's going to always work. You don't have to care about the fact that you have repeated roots or imaginary roots or whatever. For any type of partial fraction, you'll always be able to do this. On the negative side, it might require a lot of computations. This guy is fairly straightforward, but when you start having like a partial fraction of like 3 or 4 blocks, going by brute force is definitely going to explode the number of computations you're going to be doing. So let's look at the minimal computations approach. The idea is that when we're looking at solving for A, we can multiply our rule block by the denominator of A, choose S such that the denominator of A disappears, and everything that has been multiplied by the denominator of A and hasn't been simplified away is going to go to 0 as well. So let's see how that works. We multiply everything by S plus 1 squared. Then we retrieve A plus BS, because S plus 1 squared cancelled out, A equal to A, capital A, because S plus 1 squared cancelled out, and now we have plus B times S plus 1. This equation is valid for any value of S. So we can choose the value of S that arranges as most, and in this case we're going to choose the root of S plus 1 squared, that is S equals minus 1. That means that B just gets multiplied by 0, other S's also get specific values, and on the side of our unknowns, every other term except A is going to be cancelled out. So we can find A fairly straightforwardly. What's the con side of that? Is that to find B, we still have to go for the brute force approach, because the denominator of B is a part of the denominator of A, so this approach doesn't work in the generality that we want it to. But it's going to be very helpful when you have different roots. Let's go back to the example so we can apply the split that we just did. We know that the Laplace transform is linear. That means that the inverse also must be linear. So we can split this in 2 terms. And here we know what to do. So the partial fraction approach really allows you to break your problem into separate elements that you can handle more easily. And here it's just a matter of just replacing back the values that we started with. Let's go to a second example. It's again second order, but the coefficients have been changed. We go first step, we do the Laplace transform. So we have the Laplace transform of the second derivative, minus 4 the Laplace transform of the first derivative, minus 12 Laplace transform of y. The right-hand side is the Laplace transform of 0, and we know that's 0 as well. So we apply the same formulas we applied last time, and the same boundary conditions we have inserted. So we simplify as we did last time, and we introduce A and B just to not keep track of all the y0s and y1s. And we notice that the polynomial in S multiplying the Laplace transform of y, it's actually the characteristic polynomial. It's always going to be the case. So, but the coefficients A's and B's on the right-hand side are going to change, so be careful with that. But now we have an explicit formulation for the Laplace transform of the solution of the ODE. So let's use the inverse Laplace transform of it. We split our second order polynomial in S in its 2 roots, and we know that then we can use partial fractions to take the inverse of the Laplace transform, and we have solved it. Now it's just a matter of finding capital A and capital B such that everything works out. So let's look at the partial fractions again. And here, because there are 2 different roots, no repeated roots, we can use the minimal computation approach. To find capital A, we multiply everything by S minus 6. Then we compute it at S equal to 6. Then the fraction with B over S plus 2 is going to be multiplied by 0, and we have a formula for capital A. And we're going to be doing exactly the same to find B. We multiply everything by S plus 2. We compute it at S minus 2, the root of the denominator of B. And here we have an explicit formula for B. So here's our final solution, except that A and B always were defined as based on the boundary conditions. So here it is, an explicit formulation based on the boundary conditions that we have introduced. Let's have some more examples on applications of the Laplace transform. So let's look at something that we weren't able to solve yet. The spring mass system with forcing. So up to now, we haven't been able to solve, in generality, non-homogeneous functions. We have always needed the fact that the right-hand side was exactly 0 in order to have our computations flow. But this is not needed for the Laplace transform anymore. We can really go in a much more generality than we used to. So this is the spring mass system. So you have a mass that is connected to a wall with a spring, and we're forcing the mass away from the wall with a certain force. And we have introduced this force that is like a product of a cosine. So we are introducing this capital omega frequency of the forcing. So the forcing is really not like nasty with respect to what we were used to have. It's a periodic function, it's non-zero, but we're still gonna be looking at it and solve it with the Laplace transform. So let's remind yourself, when you have non-homogeneous problems, your first step is to solve the homogeneous problem, and then you look for a partial solution with the forcing term. And the full solution is a combination of the solution of the homogeneous problem and the partial solution. We can use the Laplace transform to also find the solution of the homogeneous problem, but it's usually faster to just use characteristic polynomials. In this case, in particular, we have constant coefficients for the homogeneous problem. So I'll just assume you'll have used the method of characteristic polynomials to find the homogeneous problem, and we're gonna go through it very fast. So you take the homogeneous problem, you replace the derivatives of x by powers of lambda, you solve for lambda, and in this case lambda is purely imaginary, so we're going to write it as plus or minus imaginary number times small omega, where omega squared is k over m. And then we have the homogeneous solution. There is a typo in here. One of the two powers should be negative. And this, through the Euler transform, gets to be a sum of a cosine of omega t plus sine of omega t with two different constants. So let's go into looking for the particular solution. Step 1, we use the Laplace transform. So we replace x second and x by their Laplace transforms. Notice that all the extra terms given by the formula of the derivative of the Laplace transform based on initial conditions can just be forgotten about, because we're just going to assume that in the homogeneous part of the solution, capital A and capital B will be shifted to adapt to whatever initial condition is given. So in this case, we can just choose the initial conditions that we like the most for the particular solution. So in this case, I just chose all of them to be trivial, so 0, so I don't have to drag them along while I'm computing things. So I take the Laplace transform of the cosine of capital omega t. We get a fraction s over s squared plus capital omega squared. And now we've solved for capital X. And we have this formula, explicit formula for it, fairly straightforwardly. And now we have to use the inverse Laplace transform on that formula. So let's go. We have that the particular solution is the Laplace inverse of this big fraction. First thing we can do is just take f0 over m out of our inverse Laplace transform because the inverse Laplace transform is linear. So we can do that. And then we want to use repeated fractions, partial fractions. I claim that this is the solution when you're using partial fractions, and I encourage you to try it out. And now that we have the inverse of the Laplace of two simple equations, we can recognize them as being equations of the cosines, and here we have our partial solution. A fraction based on the amplitude of the forcing term over the mass times the difference between omega and capital Omega times cosine of capital Omega t plus cosine of omega t. And now we have the homogeneous solution, we have the partial solution, and we just sum them all together. And we notice that the cosine of small omega t can just be merged with capital A cosine of omega t. A is a value we don't know yet, so adding an extra constant on top of a value that we don't know yet is not going to change our approach. So this is our full solution for the problem. I hope you noticed something that I've been sweeping under the rug for the last couple of minutes, that dividing by the difference between two positive numbers might be a problem. So I'm gonna state that when small omega is equal to capital omega, we will have a big problem. In particular, this function is not valid anymore. The solution, if you have the two omegas being equal, is fairly different. The partial solution is t times sine omega t. What is the problem with a solution like that? Well, the first solution that we have when the two omegas were different is a sum of sines and cosines. So it's something that is oscillating over time, but always within given bounds. While this new solution, it's going to have an amplitude that keeps increasing over time because the sine is multiplied by the time itself. This is usually not something you want. It might give major side effects on the long run, being actually not that long. If you're interested, I would encourage you to Google for the Tacoma Bridge. And we're going to be talking about this topic a bit more in the next video.